Okay, welcome to the deep dive. We've got a stack of material in front of us, and our goal is simple. Plunge in, extract the absolute most important knowledge nuggets, and surface with the essentials you need to be well-informed.
And today we're tackling a really fundamental concept in quantum mechanics, one that's been, debated and scrutinized for over a century. Quantum jumps.
Quantum jumps.
Right.
We sort of picture electrons leaping between orbits and atoms, emitting light. Sounds simple enough, maybe. But the history and the reality, according to our source, is packed with surprises and some pretty fierce arguments.
Yeah, our main source for this is a scientific article called Quantum Jumps, Schrödinger's Objections and the Contemporary Points of View.
And what's great about this article is it really gives us the whole arc. It starts with the initial idea, the deep skepticism it faced, especially from giants like Erwin Schrödinger, and then walks us through the modern experiments that finally answered questions that seemed almost, well, philosophical for decades.
Exactly. So our mission today is to trace that story, understand the core idea, explore that famous historical tug of war between Bohr and Schrödinger, and then unpack what the latest experiments actually show about how these jumps happen.
Okay, let's jump right in then. Starting at the beginning, the source takes us back to Niels Bohr's model, 1913.
Right, Bohr.
Mm-hmm.
He proposed that electrons didn't just zip around the nucleus any old how. They could only exist in specific, discrete energy levels,
What?
orbits.
And the idea was when an atom absorbed energy, an electron would kind of hop up to a higher energy level.
Mhm.
And when it dropped back down, boom, it emits a photon, a little packet of light. This explained why, when you look at the light from atoms, like a neon sign or something,
Or a star, yeah.
right, you don't see a smooth rainbow. You see these specific sharp lines of color, the atom's fingerprint, basically.
And those sharp lines, they perfectly match the energy differences between Bohr's proposed orbits. A jump between level A and level B always gave off a photon with exactly the energy difference between A and B. Very specific.
But here's the catch in 1913. You couldn't actually watch one atom do this, right?
No way! All the experiments are done on, huge clouds of atoms. Billions and billions of them.
So what you saw, the spectrum, was the combined average effect of countless electrons jumping in countless atoms all at once.
You couldn't isolate a single event, a single electron in a single atom. Impossible back then.
And this is where the doubt started creeping in, wasn't it? The source mentions many physicists kind of thought these jumps weren't, real physical things happening.
Yeah, more like convenient fictions, mathematical tricks just to make the theory fit the data, fit those spectral lines they observed.
Not actual events in individual atoms.
Precisely. And perhaps the most prominent and loudest skeptic was Erwin Schrödinger.
Ah, Schrödinger. The article talks about his visit to Bohr in Copenhagen in 1926. Bohr apparently tried really hard to persuade him.
He did, but Schrödinger just wasn't buying it. He had some really fundamental objections.
Okay, what were his main sticking points then?
Well, the source highlights two big ones. The first one went right back to classical physics, to Maxwell's equations for electromagnetism.
Ah, the standard rules for electricity and magnetism, the ones that work perfectly for, well, everything else at the time.
Exactly. And Maxwell's theory was crystal clear. If you have an electric charge, like an electron accelerating, say, by orbiting a nucleus, it must radiate energy continuously.
And if it radiates energy, it loses energy.
And spirals into the nucleus. The atom should collapse almost instantly. But obviously, atoms are stable. Bohr's model just said electrons in these special orbits don't radiate.
So Bohr just kind of waved away Maxwell's equations for these specific orbits.
Pretty much. He postulated stability without explaining why classically they should be stable. Radiation only happened during the jump, according to Bohr.
That sounds like a massive contradiction. The source mentioned someone else had the same issue early on.
Yeah, Max von Laue. Even back in 1913, he apparently said something like, "This is nonsense. Maxwell's equations are always valid. An orbiting electron must radiate." It was a major hurdle.
Okay, so how did quantum mechanics eventually start to deal with that problem? Why don't electrons spiral in?
Well, this is where the whole wave nature of the electron becomes absolutely critical. In quantum mechanics, electrons aren't just tiny balls whizzing around. They're described by wave functions.
Wave functions.
Okay.
Right, so they have wave-like properties.
Exactly. And inside an atom, these wave functions form standing waves.
Standing waves, like the vibrations on a guitar string when you pluck it. You get specific notes, specific patterns.
That's the perfect analogy. These electron standing waves are specific, stable patterns that kind of fit around the nucleus, Bohr's discrete energy levels. They correspond exactly to the energies of these allowed standing wave pattern.
Okay, so the electron isn't really orbiting like a tiny planet, constantly accelerating and radiating. It's more like a stable, spread out wave pattern.
Right, and these specific standing wave states inherently don't radiate energy continuously like an orbiting classical charge would. So the wave picture resolves that specific conflict with Maxwell's theory about the stability of the atom.
But the source makes a point to say, the electron itself is still pretty weird, right? This whole particle wave thing.
Oh, absolutely. It's still fundamental. Is it a particle? Is it a wave? Well, it behaves like both, depending on how you look. The source quotes Frank Wilczek calling the electron ideally simple and unimaginably complex. It is precisely understood and utterly mysterious. That duality is still, at the heart of quantum mechanics.
Okay, so the wave idea helped explain why atoms don't just collapse. But that still leaves Schrödinger's second major objection.
Mm-hmm.
That was about the jump itself, yeah.
Exactly. This was maybe even deeper for him. He basically asked, okay, if these jumps happen, what actually goes on during the jump? Is it instantaneous or does it take time?
And why was that such a big deal for him?
Well, think about it. If the jump, the energy change, happens gradually, smoothly, you'd expect the light emitted to cover a smooth range of frequencies, like a smear, not those super sharp spectral lines they observe.
Oh, right. Sharp lines imply a very specific energy change.
Exactly. But if the jump is instantaneous, like Bohr suggested, how does the electron do that? How does it disappear from orbit A and instantly appear in orbit B? What path does it take? What laws of physics govern that split second?
It sounds like he just found the whole concept physically unbelievable.
Totally. The source says he called the whole idea of quantum jumps nonsense. He just couldn't fit it into any picture of continuous, understandable physical processes.
And Bohr's description back then probably didn't help Schrödinger's discomfort. Bohr said the jumps were sudden, instantaneous, and happened at random moments.
Yeah, appearing without a cause at some unpredictable instant. This randomness, this lack of a specific trigger for when a jump would happen, was a huge philosophical problem for physicists like Schrödinger and Einstein. They really wanted deterministic cause and effect laws underneath it all.
And Schrödinger also pointed out, again, that you couldn't even see a single atom back then.
Right. He felt physicists were just looking at statistics from huge groups of atoms, scrutinizing records of events long after they have happened, as the source puts it. So talking about what one electron did during a jump seemed like pure, untestable fantasy to him.
But even back then, there were some early experimental hints that maybe the jump wasn't perfectly instantaneous, even if it looked that way.
That's right. Some clever experiments using interferometry looking at how light waves interfere with each other showed something interesting. The light coming from atoms, say from a sodium lamp, wasn't an infinitely long continuous wave.
Okay.
It came in chunks, finite segments, or wave trains that were maybe half a meter to a meter long.
And light travels at the speed of light, so if the wave train has a length.
The process that created it must have taken some amount of time, not zero time. A meter-long wave train means the emission process lasted for roughly 3 to maybe 10 nanoseconds. Incredibly fast, yes, but definitely not instantaneous.
So even early on, there was evidence that the energy change, the emission, had some finite duration, however short.
Exactly. The source notes that even Schrödinger had to concede, hypothetically, that if jumps were real, the finite length of these wave trains implied the energy change must have a definite duration.
Okay, so hints were there, but actually seeing a single jump, that was still out of reach for decades. How did we finally get there?
Right, now we jump forward, big time, to 1986. This was a landmark year, really, because experimental techniques had improved dramatically.
This is when they figured out how to trap and cool single atoms, or ions usually.
Exactly. Using lasers and electromagnetic fields, they could isolate and hold a single ion and cool it way down so it wasn't jiggling around too much. And finally, they could watch one single quantum system.
So what do they set up? The source mentions using an ion like mercury with specific energy levels.
Yeah, typically they'd use an ion with a convenient set of 3 energy levels. There's the ground state, the lowest energy, then a strong excited state when the electron jumps too easily and decays back from very quickly.
Okay, fast transition. Lots of light if you drive that one.
Right. And then the crucial third level, a weak or metastable excited state.
Metastable, meaning it's kind of stable, but not perfectly. The electron gets stuck there for a bit.
Precisely. Stuck is a good word. The strong state might decay in nanoseconds. The metastable state in these experiments could last for maybe a tenth of a second. That's an eternity in atomic terms.
Okay, so ground state, fast-decaying bright state, and a long-lived dark or metastable state. How did the experiment work?
They used two lasers. One laser was tuned to constantly drive the transition between the ground state and that strong, bright state.
So electron jumps up, falls down, emits a photon, jumps up, falls down, over and over.
Exactly. A very rapid cycle, billions of times per second maybe. This produces a steady, bright stream of photons. The ion just glows intensely. Like for the mercury ion they mentioned, maybe 100 million photons per second. Very bright.
Okay, and the second laser?
The second laser was tuned to occasionally nudge the electron from the ground state up to that long-lived metastable state. This jump was much less likely, but it could happen.
And what happens if the electron does land in that metastable state?
Aha. That's the key. Once the electron is sitting in the metastable state, it's stuck there for that relatively long tenth of a second. And crucially, the first laser, the one driving the bright fluorescence.
Can't affect the electron if it's in the metastable state.
Exactly. That laser's frequency is wrong for exciting it from the metastable state. So the rapid cycling that produces all the light just stops.
And stops glowing. It goes dark.
It goes dark. And what they saw when they watched a single trapped ion for a while was amazing.
What did they see?
They'd see this continuous bright fluorescence for seconds at a time. Then suddenly, poof, the light would switch off, completely dark.
For how long?
For about that characteristic lifetime of the metastable state, maybe a tenth of a second on average. And then, just as suddenly, poof, the bright light switched back on.
That on-off switching, that blinking,
Yeah.
that was the quantum jump.
That was the quantum jump. Going dark meant the electron had jumped to the metastable state. Coming back on meant it had jumped back down to the ground state, allowing the bright cycling to resume.
Wow. So direct visual evidence of jumps in a single atom.
Undeniable proof. Quantum jumps were real, physical events happening to individual atoms, not just some statistical effect in large groups. It blew away that old skepticism about their existence.
And these 1986 results, particularly the jump back from the metastable state, they seemed to fit Bohr's original picture, didn't they?
In a way, yes. When the ion became bright again, that jump back looked sudden, instantaneous on their timescale. And when it happened, seemed random. It supported the idea of jumps being sudden and probabilistic events.
Could they see what Schrödinger really wanted to know? What happens during the jump itself, in that tiny fraction of a second?
No, not with those experiments on natural ions. The switch from dark to bright, or bright to dark, still looked instantaneous. The actual process of the transition remained hidden in the dark, so to speak.
Okay. Which brings us to the really recent, cutting-edge stuff described in the source. The 2019 experiments.
Yeah, this is where things get even wilder. These researchers took a different approach. Instead of a natural atom, they built an artificial atom.
An artificial atom, like an engineered system.
Exactly. A superconducting circuit, something macroscopic you can build on a chip, but designed very cleverly so that it behaves quantum mechanically like an atom. It has discrete energy levels analogous to the ground state, the bright state, and the dark metastable state of the ion.
What's the advantage of using an artificial one?
Control. Because it's a larger engineered system, you can hook wires up to it, essentially. You can probe it and measure it with much higher precision and speed than a tiny natural ion floating in a trap.
Okay, so they set up this artificial atom with its ground, bright, and dark states. What did they find when they looked at the jumps? This is where we get the details Schrödinger wanted.
This is exactly where we get them. They used microwaves to drive the transitions, similar to how lasers were used before, and they monitored photons emitted from the bright state. But with their enhanced control and measurement speed, they saw things no one had seen before.
Like what? Did the jumps still look totally random and sudden?
This is the first amazing thing, no. They found that just before the system jumped from the bright state to the dark state, there was always a detectable little hiccup.
Hiccup.
Yeah, the emission of photons from the bright state would briefly slow down, a sort of pause.
A warning signal. A precursor pause, as the source calls it.
Exactly. A brief period of hesitation indicating a jump to the dark state was imminent. This immediately throws a wrench in the idea of the jump being totally random and uncaused at the moment it happens.
So it might still be random when that pause starts, but once you see the pause?
The jump to the dark state is coming. The source notes, it seems deterministic from that point on. Once that precursor is detected, the system is committed to the jump, even if you stop driving it externally.
Wow. So randomness in the timing of the trigger signal. but a deterministic process once it starts. Okay, that's one huge finding. What else? What about the jump itself? Still instantaneous.
And this was maybe even bigger. They could use clever tricks, like briefly turning off the measurement during the suspected transition time to avoid disturbing it too much, and they found the jumps were not sudden at all.
Not sudden. Not leaps.
No, they were gradual, continuous evolutions. They unfolded smoothly over a timescale of a few microseconds.
Wait, gradual. But what about the sharp spectral lines? Schrödinger's old problem. How can a gradual energy change give a sharp frequency?
Right, it seems like a contradiction. But the modern view, supported by these experiments and theories like quantum trajectory theory, is different. The gradual evolution they saw isn't the system slowly sliding down an energy hill, it's the system transitioning through a superposition.
Superposition, meaning it's kind of in both the initial bright and final dark states at the same time during the jump.
Exactly. It's a mixture. The source explains they could even reconstruct this process, like taking snapshots. They could see the probability of being in the bright state smoothly decrease, while the probability of being in the dark state smoothly increased over those few microseconds. It flows from one state to the other through this blended superposition state.
So it's not like flipping a light switch. It's more like using a dimmer switch. But the dimmer knob represents the mixture of on and off states.
That's a decent way to picture it. It's a continuous trajectory through this abstract space of possibilities, landing eventually in the final state.
Okay, gradual evolution through superposition, that's mind-bending. And the control they had with this artificial atom allowed something even crazier, right? Something about stopping the jump.
Oh, yeah. Because their measurement and control systems were so incredibly fast, they could actually react during that microsecond transition. They could essentially catch the jump in progress.
Catch it, what could they do?
They could effectively freeze it mid-flight, or even reverse it, make it go back to the initial state after the transition had already started.
Reverse a quantum jump, how's that even possible?
It's related to something called the quantum Zeno effect. The basic idea, maybe oversimplified, is that if you keep measuring a quantum system very, very frequently, you kind of force it to stay put. You disrupt the natural evolution that would lead to a transition.
Because each measurement collapses the wave function, resetting the process.
Something like that. The source mentions the probability of making a transition actually grows quadratically with time, meaning it starts very slowly. So if you measure extremely quickly, the chance of it having jumped between measurements is tiny. Each measurement essentially pins it back down, preventing the gradual evolution from completing.
Yeah.
By carefully timing these interventions, they could halt the jump or even steer it back.
So in this artificial system, they had enough control to literally pause or rewind a fundamental quantum process as it was happening. It's a stump.
It really is. It gave them an unprecedented window into the dynamics during the jump, the very thing Schrödinger despaired of ever seeing.
Okay, let's try and tie this all together. The 1986 experiments using natural ions, they were crucial because they proved quantum jumps exist as real events in single atoms.
Right. They settled that fundamental debate. Jumps are real, observable, and from the outside they looked sudden and random, particularly the jump back from the metastable state.
Then, the 2019 experiments with the controllable artificial atom, they peeled back the curtain. They answered Schrödinger's deep questions about what happens during the jump.
Exactly. They revealed this hidden structure, a precursor warning signal, then a deterministic, gradual, continuous evolution through a superposition of the initial and final states, taking a few microseconds.
So the picture we get from the source is that while jumps in natural atoms might appear instantaneous and random, the underlying mechanics, at least as seen in these highly controlled artificial systems, are actually quite different. There's this hidden deterministic evolution happening.
That's the journey the source takes us on, from being dismissed as nonsense to being directly observed, and now to having the intricate dance during the jump itself revealed. It's a profound shift in understanding.
So why does this matter to, someone listening? Why should you care about the nitty-gritty details of how an electron, or an artificial circuit, makes a quantum jump?
Well, on one level, it's about fundamental knowledge, isn't it? Understanding how the universe actually works at its most basic level. These experiments move quantum mechanics from abstract equations to things we can actually see and apparently even influence in real time.
And that ability to see, predict with the precursor, and maybe even control these jumps.
Yeah.
That sounds like it has practical implications too.
Oh, absolutely. Think about quantum technologies. Quantum computing, quantum sensing, secure communication. They all rely on manipulating individual quantum states and controlling transitions between them very precisely.
So understanding how jumps really happen and showing you can potentially predict or even steer them, like in the artificial atom.
That's hugely significant. It suggests a level of control over the quantum world might be possible that could underpin future technologies. These aren't just cool physics experiments, they're laying groundwork.
Wow. Okay, so this deep dive really has covered a lot of ground,
Hmm.
from Bohr's initial controversial idea and Schrödinger's deep skepticism.
Through that landmark 1986 proof that jumps are real events in single atoms.
And finally landing on these incredibly detailed 2019 experiments, revealing the surprising reality inside the jump, the precursor signal, the gradual evolution through that superposition state, and even the potential for real-time control.
Yeah, the key takeaway from the source seems to be quantum jumps are definitely real. But while they might look sudden and random from the outside, especially in natural atoms, the cutting-edge experiments on these artificial systems show us there's a hidden layer, a deterministic trigger, a smooth transition, challenging that old notion of an instantaneous leap.
But it's important to remember, as the source points out, that super detailed view and that amazing control that's currently only demonstrated in these macroscopic engineered artificial atoms, right?
That's the current frontier, yeah.
Yeah.
Do natural atoms behave exactly the same way during their jumps? Can we ever achieve that level of prediction and control with them? Those are still open questions. What mysteries might still be hiding inside the jumps of regular atoms?
Right. So here's a final thought for you to chew on, drawing from that incredible control they achieved. The ability demonstrated in those 2019 experiments to actually pause or even reverse a quantum jump while it's happening in an artificial atom, something Bohr or Schrödinger would have found utterly unimaginable. What does that level of potential control over fundamental quantum events really imply for our future understanding and maybe manipulation of the quantum world?
Subscribe for more.